Hello and welcome, class, to another lecture where here we are going to be beginning chapter 14 in our textbook, the 4th edition of Burge and Overby's Chemistry Atoms First. We are taking a step back to chapter 14 because, as a reminder, 15 was all the updated, the more advanced discussion of thermodynamics, where in chapter 15, the primary topic of conversation was entropy and how entropy can be used to understand the spontaneity of a chemical reaction. So chapter 14, we're going to be building sort of off of this energetic discussion. Namely, we're going to be asking the question, if a reaction is going, how fast is it going to go? So this is really what the study of kinetics is. It's not just about kinetic energy, but also about the speed of the reaction. All right, so chemical kinetics is a huge topic in chemistry. In fact, we're going to be spending at least 5 days talking about this. We're going to be spending a fair amount of time in chapter 14. So chemical kinetics studies the rates at which reactants are consumed and products are formed. So there are a couple of different ways that we can observe and study a reaction. We can either observe the reactants as they disappear slowly over time or quickly over time, or we could observe the products as they are beginning to be generated. The decision, like which one do you actually observe, is going to essentially come down to like which is the most convenient to observe. For example, if we are studying, let's say something like copper sulfate as it is being generated in solution. So copper sulfate, we'll say, is the product. It's going to be pretty easy to observe the generation of copper sulfate because it is a very rich blue color. So this is going to be, or this type of characteristic, this type of observation is going to be what helps us to decide what we're going to be paying attention to, reactants or products. So a particular reaction may be spontaneous, again, as we've discussed in our previous lectures, the previous chapter. Spontaneity has to do with the entropy of the universe being greater than 0, or another way to look at it is our delta G has to be less than 0. But this chapter, this conversation is all going to be about, will the reaction start? And once it's started, how fast is it going to go? So spontaneity has to do with after the reaction has been started, will it proceed? Will it continue of its own accord without any additional necessary energy being put in? But the question of will it start really is more of a kinetic question, not necessarily a spontaneity question. And so we're going to be discussing will the reaction start as well as how fast it will go in great detail throughout this chapter. So we're going to keep coming back to these questions multiple times and seeing how we can observe them and study them from a number of different perspectives. So where we are going to start, like the first possible answer, the first perspective that we are going to observe, is that of collision theory. Collision theory states that in order for a reaction to take place, chemicals must collide. Well, this makes perfect sense, right? If you have an oxygen atom in one corner of your dorm and a nitrogen molecule in the other corner of your dorm, how are they going to react and create any type of like chemical bond if they're too far apart to even know that the other exists? So collision theory really does focus on the fact that these molecules not only must be in close distance, but they must be able to come into physical contact with each other. All right, the reaction rate, or the speed of the reaction, is going to be directly proportional to the number of what we call effective collisions per second. Now, we could observe reaction rates per any unit of time, really. We could look at minutes, we could look at hours, we could look at days, but the standard unit of time is the second, so we're going to be really consistent in general chemistry, at least, and observe our reactions in terms of seconds. So how do we increase the rate of our reaction? Well, we can either increase the number of effective collisions that we can make, which numerically is going to increase the rate, or we could decrease the amount of time that a reaction takes place in. So both the count of effective collisions and the time are going to play a huge factor or play a huge role in what the overall rate of the reaction is going to be. So we're going to spend most of our time today just observing what it means to be an effective collision. We're going to also be referring to effective collisions in the context of collision theory throughout this entire chapter. Again, coming back to answering the long-standing question of how do we know how fast a reaction is going to go? Well, what is an effective collision then, right? If we need more effective collisions to speed up our reaction, it's going to be important to know what an effective collision even is. An effective collision is a collision that is going to result in a chemical reaction. So an effective collision will cause a chemical reaction to occur on a very small scale between a handful, if not just a couple of molecules. And so the more effective collisions we have, the more the reaction is going to progress, and therefore the faster it's going to go. All right, so in order to have an effective collision, one, the molecules must have proper orientation. In other words, it's not enough for them to just bump into each other. They need to bump into each other facing the right way. So for example, if we observe this carbon monoxide coming into contact with this oxygen molecule, where here we have these like action lines, there's a collision happening here, it looks like the oxygen of one molecule is coming into contact with the oxygen of the other molecule. Now, if these things do collide with sufficient energy, we might see some type of reaction occur, but it's not the reaction that we are aiming to have. Therefore, we are going to label that no reaction here exists. These two molecules did not come into contact in such a way to create the proper products. In order for these two things to come into contact and form, as we can see over here, carbon dioxide and oxygen atom, we're going to need the carbon in this carbon monoxide to come into contact with the O2 gas. Only here would the bond between the O2 be broken. A bond would then form between the oxygen and the carbon, and our sole oxygen here is going to then be the remaining oxygen on the product side of this reaction. So if the molecules don't arrange themselves properly as they are coming into contact with each other, we might have enough energy to actually break some bonds and reform some other bonds, but if the bonds aren't lining up correctly, nothing's gonna happen. All right, rule number 2, the molecules must also have sufficient energy to activate the reaction. In other words, we need to meet the energy requirement to break bonds. We need to make sure that we are putting in the energy necessary to actually break the bonds that need to break, and therefore will have the ability to reform the bonds that need to be made. If we don't have the necessary energy to put in, it doesn't matter if the molecules orient themselves in the right way, they're just going to bump into each other and bounce off of each other and not form any products if bonds can't break. So an effective collision, one that results in a chemical reaction, must result from proper orientation of the molecules, bumping into each other with sufficient energy to actually get the reaction going. So let's talk about the energy requirement a little bit more before we return to discussing effective collisions. Now, we've defined this energy once before, but it was a long time ago in chapter 10. The energy necessary for molecules to begin reacting is known as the activation energy and is represented by variable capital E with a subscript of a capital A. A for activation, big E obviously for energy. We can think of this energy as that initial spark that is necessary to start the reaction. Now, this can literally be a spark, as is often the case when it comes to combustion reactions, but it could also be stirring or heating or electrocuting. the most effective input energy is definitely going to depend on the type of reaction we are actually working or observing. Now, this activation energy can also be visualized in a reaction diagram like we can see here. This is a reaction potential diagram. And we have seen this type of diagram a couple of times before, where energy is present on the y-axis and time, or the progress of the reaction, is illustrated here on the x-axis. And regardless of exactly what the reactants and the products are, there's always going to be a little bit of input energy that we need to supply to the reaction in order to get it going. This is the activation energy, and it is required according to collision theory. We will come back to discussing the activation energy in more detail in a little bit. I believe in part 3 of this specific lecture series, we're going to come back to quantifying our activation energy. How do we find the activation energy? But for now, we're just going to talk about it more qualitatively in the context of collision theory, and just acknowledge that we need some type of energy to put in order to get the reaction to move forward. All right, so we're going to spend the rest of our day then today talking about what factors, what observables will make an impact on the number of effective collisions that we can have while undergoing a chemical reaction, and therefore how we can increase the rate of the reaction. So first and foremost, the rate of a reaction is going to be dependent on the physical state of your reactants and products. Specifically, if our reactants could be a solid, a liquid, or a gas, we would conclude that the gas, because it has free range of motion, will most likely supply us with an effective collision, since the molecules can actually move around. Right, if you take two solids and sit them next to each other, the odds of them reacting are very low. Particularly if we need to put in some type of activation energy, we're going to have to put in even more energy to get these solids mixing with each other and reacting in some way. This is oftentimes why we take solids and dissolve them in liquids to increase their mobility and therefore increase the chance of making an effective collision. Gases already have that free range of motion, so if you want a reaction to progress quickly, just make sure that your reactants are either in aqueous or gaseous form. Specifically, gases would be best, and we are going to increase the chances of making an effective collision, therefore speeding the reaction up. All right, the next variable that we're going to observe that can have an impact on the rate of your reaction is the surface area of your material. Now, here we have two different pieces of zinc. The first on the left is a solid chunk of zinc, just zinc solid. We can see that it is metallic. It is fairly shiny. We'd say it's somewhat lustrous. It's silver in color. Looks just like any other kind of metal that you would be able to find on the periodic table. What we have illustrated on the right is known as zinc mesh or zinc powder. These two terms can be used interchangeably, and really mesh versus powder just has to do with how fine the grain is. We still have zinc here, we've just taken it and run it through some type of shredder. It's almost like the difference between a hunk of Parmesan cheese and grated Parmesan cheese. On the right-hand side, what we have done is increase the surface area of the material. We have increased surface area. Right, by taking this material and shredding it up into a bunch of tinier pieces, each one of these granules is going to contribute to a portion or is going to contribute a fraction, right, of the total surface area across this entire material. If the zinc is stuck in solid form, as we have illustrated on the left, only the zinc atoms on the outside are going to contribute to the surface area. So we actually have a decreased surface area here. And if we have a decreased surface area, we have a lower chance for particles to come into contact with each other. Right, again, what we're looking at here is how to increase the number of effective collisions. With greater surface area, there is more of a chance for particles to make contact. So whether we're stirring like this solid into an aqueous solution, or if we're electrocuting it in the presence of another metal nearby, because there is an increased surface area, we are actually going to see an increase in the number of effective collisions according to collision theory, and therefore we'll see an increase in the reaction rate as we increase the surface area of the material. All right, speaking of, though, making things or turning them into an aqueous phase, our reaction rate is also going to depend on concentration. Now, this is a big one. We are going to be focusing on the concentration dependence of our chemical reactions, like the kinetics of them, in part 2 of this lecture. So we will be returning to this concept, this definition, in more detail, more quantitative detail in part 2. For now, we are just going to observe the fact that an increased concentration, like we have here on the right, a greater molarity, has more stuff in solution, and therefore is going to increase the odds, greater chance, for making contact. And of course, if we're increasing the chances for particles to make contact with each other, since now they're in closer quarters, they have less distance they need to travel, there's a higher chance that they're going to bump into each other just with the natural kinetic motion in an aqueous solution, we are also going to be increasing the number of effective collisions and therefore increasing the reaction rate. This is incredibly important because sometimes also, like, before we get ahead of ourselves, I know we're looking here at ways to increase the reaction rate, but it's also important to recognize that sometimes we don't want the reaction to go fast, right? Sometimes we want the reaction to slow down, particularly times when the reaction would otherwise be explosive, either because too much heat is being generated, maybe fire, right, through light and heat in combination is being generated, maybe so much gas is being generated as a product that it could literally cause an explosion within your reaction vessel if the pressure gets to be too high. Right, so the concentration dependence we will be, again, observing in more detail in part 2 of the lecture, but specifically we want to keep in the back of our minds that we don't necessarily always want the reaction to go fast. Sometimes it's more about being able to control the speed of the reaction, where yeah, sometimes we want it to go fast, but sometimes we don't, and we can control the concentration of the solution to be able to manipulate the rate of our reaction. Similarly, another variable that we can control quite easily inside of the lab setting is temperature. Now, temperature we will be returning to in part 3 of our lecture to observe again in more quantitative detail, and we will be observing the temperature dependence of our reactions also in the context of our discussion of the activation energy. So we're going to be putting temperature and activation energy together in a couple of days. And specifically, the reason why is it turns out that temperature and activation energy are related to one another in the or in how we measure our reaction rates. All right, so how the temperature, though, has an impact on our reaction rate is if we speed up the reaction. So if we heat up either the gaseous sample, as is being illustrated here, or even the liquid or the solid sample, there will be more molecular motion. Right, an increase in temperature is literally a means to increase the molecular motion. If we're increasing the motion, obviously the chances of particles coming into contact with each other is going to increase. Therefore, we also are going to have a means to increase the number of effective collisions. And again, just like the concentration, sometimes we don't want the reactions to go too fast. So in the event that we would actually prefer to slow down the reaction, we can cool the reaction down to slow down the rate as well. So we do have the means to, let's say, manipulate our reaction rate to get the desired speed of the reaction. All right, and last but not least, The reaction rate is going to depend on whether or not a catalyst is present. Now, catalysts are chemically incredibly interesting. The main reason why is that a catalyst helps a reaction to progress, but is not a reactant. So we add a catalyst to a chemical reaction, it is going to help the reaction to move faster, but it itself does not get used up in the chemical process. It's just physically sitting there and helping the reaction to move. So how a catalyst helps the reaction to progress, we will be talking about in more detail in part 5 of our lecture. You may be thinking like, well, where did part 4 go, right? Like if concentration dependence is part 2 and temperature dependence is part 3, catalysts are going to be discussed in part 5. Part 4 of our lecture, we are going to be returning to the time dependence of our reaction, since rates are effective collisions per unit of time. All right, so how do catalysts, though, if they are not a reactant, help the reaction to move forward? Well, here we have a general illustration of how an enzyme, which is a type of a catalyst, so catalyst, good example, e.g., is that of an enzyme. Something like a digestive protein, right? It's in your stomach helping your food to like be broken down faster. What this enzyme does in this illustration is pull in what your two reactants are. So here we have reactant A and reactant B, and we can see that this enzyme or this catalyst has these two like little notches inside that are going to be perfect places for A and B to take a rest. Well, coincidentally, as A and B take a rest inside of this catalyst, they are now right next door to each other and can start undergoing a chemical reaction. Effectively, what is happening here is that the catalyst itself is now bringing your two reactants, or possibly your 3 reactants, your 4 reactants, however many we have, and are going to hold them together and force them to effectively collide. So a catalyst is a way to ensure that we will get an effective collision. So as the two particles collide, our two reactants A and B, after the reaction has been undergone, the protein itself or the enzyme is going to release this new compound C, which is made up of A and B back out like into the reaction mixture. So substrate, aka the reactants, move toward what is known as the active site inside of a catalyst. The reaction then occurs in the context, like either on or in or around the catalyst in some way, which is this second picture here. And the third is that the product is going to be released by this enzyme, by our catalyst. And now we can also see that the catalyst is ready for more. This is what it means when we say that a catalyst is not a reactant. It's because if we considered this enzyme here to be a reactant, let's say we even just label it a C, or actually, I'm gonna say D, because we have a C, that's our product. It looks like A plus B plus D turns into C plus D. And as we have seen multiple times now in this chemistry course, if a reactant is also present on the product side, we just cancel it out. Right, so catalysts may not be a reactant because they are also present on the product side, but this doesn't mean that they don't get involved with the reaction. Quite to the contrary, they are very involved, they just don't get used up. They are going to be present as a product after the reaction is done and now are ready, or now is ready to take some more A and some more B to do this reaction all over again. So if a catalyst is present, we will increase the number of effective collisions that we have in solution, as opposed to if we don't have a catalyst, the reaction will take place much slower. And just to give us a little bit more of like a time scale here, we can imagine inside of our stomachs, these digestive enzymes that are catalysts being present help our stomachs to digest food within a 24-hour period. If these enzymes were not present inside of our stomachs, the hydrochloric acid inside of our stomach would not be able to digest food quickly enough to actually give us the energy that we need. So enzymes are really great at moving these reactions forward in a more timely manner to make sure that the energy that is, at least in this case with digestion, the energy that is being released efficiently. All right, well, with this introduction out of the way, I do not have any section review problems for you today, so there's no final slide after this one. But I will say, if you do have any questions on collision theory or how we can increase or even decrease, right, the number of effective collisions our reaction needs to get moving forward, please do not hesitate to let me know. If you have homework, double check and do your homework. And though this lecture may have been a shorter one, class is dismissed.